Hi, today we're going to talk about a thermodynamic quantity that we call entropy. So in Gen Chem 1, you probably learned about two different thermodynamic properties. The internal energy, delta E, or some books call it delta U, which is a measure of the total energy in a substance, and then delta H, or enthalpy, which is the total energy under constant pressure conditions, which is also equal to the heat. When you talked about these things, you talked about usually delta E or delta H because it's really hard to actually measure exactly how much energy is in an object, like a desk. But you can measure a change in energy. Let's say you take that desk and you lift it 1 foot off the floor, so you can measure the change, which is linked to the change in potential energy from lifting it. Same holds true with enthalpy. We can measure a change in enthalpy by measuring the heat that's produced or absorbed by a reaction. But if there's just something sitting there in a beaker, it's really hard to measure the total enthalpy of that substance. So now we're going to talk about another thermodynamic property that we call entropy. Now, if you've heard of entropy before, you might have heard it described as a measure of disorder. Sometimes people use that word as a synonym for chaos, but that's not really what entropy actually is. A better way to think of entropy is a measure of possibilities. How many possibilities are there? As an example, imagine that you've just gotten your keys to your new apartment and you step inside to look around before you go get the moving truck just to make sure everything's okay. And while you're looking around, you put your hat down somewhere, and later you say, "Where's my hat?" Well, you tend to have a fairly easy time of finding your hat because there aren't that many places to put it. In this case, the only horizontal surfaces are in the kitchen, so it ended up being in the kitchen. But now imagine 6 months later, you're looking for your hat. You have moved all of your stuff in there. And what's worse, it's now finals week and you haven't been able to clean for the last, 6, 7 days. And there's just stuff piled all over. And you go looking for your hat and you're like, well, I don't know where that could be. What has changed since before you moved in? Well, now there are a whole bunch of other places where you could put your hat. There are far, far more places. And so this is why we say there's higher entropy when there's more things in your apartment. So there's an equation that defines entropy as a measure of possibilities. It's Boltzmann's equation. This S here is what we use to represent entropy. So you're going to be seeing S pop up a lot over the next couple of days. So entropy is equal to K, which is the Boltzmann constant. By the way, the Boltzmann constant is related to what we think of as the gas constant, R. So basically, R as a constant is good for a mole of stuff, and K is the version when you're talking about a single particle. So the Boltzmann constant is the gas constant divided by Avogadro's number. Anyway, entropy is the Boltzmann constant times the natural log of W, which is the number of possibilities. What does it mean, the number of possibilities? At this point, many books will start describing possibilities using things like a deck of cards. And that doesn't always translate in people's minds as to what that could mean in terms of molecules. So let's actually look at some things that happen with molecules in terms of possibilities. So if you have a molecule of gas, as you increase the volume, you increase your entropy because there are more possibilities for where those gas molecules can be. As an example, say we have a molecule of HCl gas, and say that is contained in a box that is just barely big enough to fit the molecule inside. There is only one possibility for how that HCl can be oriented. But you can imagine if you make that box suddenly 4 times bigger, now you can have your HCl here, you can have it here, you can have it here, you could have it here. And then, of course, there are possibilities I haven't even drawn, like rotating it so that it's 90 degrees and then putting it that way at the bottom of the box, the top of the box, the middle of the box, etc. There are a whole bunch more possibilities in terms of where it can be positionally. We talk about entropy increasing with temperature. Let's think about why that might be. Remember that temperature is a measure of the average kinetic energy. And so as temperature increases, the movement of a molecule increases. And there are many possibilities for how that movement can increase. And often it's a combination of all these different sorts. So for example, there's a sort of movement that we call translation, which is the molecule actually moving around. We see that a lot in gases. There's the sort of motion we call rotation, where the molecule is spinning. And I've demonstrated the obvious way for the molecule to spin in 2 dimensions, but it could also roll around a couple of other axes. There's also the sort of movement that we call vibration or stretching, where the bonds are actually moving, which allows the shape of the molecule to change slightly over time. So all of these things are going to increase with temperature, and there are many combinations of how this can be happening. So you might get a certain sort of vibration along with translation. You might get a different sort of vibration with translation, or you might get rotation with translation. Many, many ways that things can move. So all of those are related to possibilities with molecules. Usually, if we have a number for entropy, that encompasses all of those different factors. How many places can it be? How can it be moving? How can it be spinning? How can it be stretching? So we've been thinking up to this point a lot about gases, which move around a lot. But let's think about a solid. Solids don't move as much, and so they tend to be lower entropy substances. Things are arranged in a nice, orderly fashion, which tends to mean low entropy in and of itself. But as temperature increases, the molecules within a solid start moving around. And so if you have a crystal structure that is regularly arranged, that becomes more and more disordered. And you might think about this if you think about, let's say, an ice cube, or at another extreme, you could say a rock. So as you heat the ice cube, it used to have a nice cubic shape and all the water was neatly arranged within it. But as you start to heat that, parts of it start to melt, and it doesn't always melt cleanly from the outside in. Sometimes you'll get these little pockets of meltwater in the ice crystal, so there's more disorder. Likewise with the rock, you might find uneven melting throughout the rock, so there's less order within the minerals in the rock. And so what's going to happen is as the temperature increases, solids are either going to turn into liquids or gases, depending on what solid you're talking about. And we know that liquids and gases move around far more and have fewer intermolecular forces holding them in shape than solids do. So entropy is going to increase. Now, I want you to think about the opposite process now. Now we're going to take something that's moderately high entropy, and we're going to start cooling it down. And we're going to keep cooling it down. As things cool down, they move less and less. And so your gas turns into a liquid, your liquid turns into a solid, all these intermolecular forces form, holding things in position. But even within a solid that is perfectly ordered, as long as you are at a certain temperature, those little molecules are still wiggling. But as you get colder and colder and colder, they wiggle less and less. And at some point, all of that motion stops. And that point is what we call 0 Kelvin, absolute zero. So the only way you can have entropy being zero is when the temperature is 0 Kelvin. So we have the third law of thermodynamics. I don't know if you've heard the second law yet. You probably heard the first law of thermodynamics, which is related to the conservation of energy. But I'm going to introduce the third law first. The third law of thermodynamics tells us that the entropy of a perfectly ordered crystal at 0 Kelvin is 0. Perfectly ordered means there's no little things thrown into the middle of it. So, for example, you might have a diamond, but some diamonds have little air pockets in them. That would not be perfectly ordered, right? So a perfectly ordered crystal has all the atoms in the right places with no substitutions, etc., etc. So if you get something that's perfectly ordered and is also not moving because you're at 0 Kelvin, it has 0 entropy. We can extrapolate from this, though, and think about how things move as they start to heat up. And because we understand how things move and rotate and vibrate, we can actually calculate the total amount of entropy in a substance as you move above 0 Kelvin. And so entropy is actually a thermodynamic property for which we can, at any temperature, say exactly what the entropy of that substance is. And this makes entropy unique amongst all our thermodynamic properties. And so if you look in the back of your book, what you're going to find is you're going to find a table of thermodynamic properties. And in the book that we're using at the time I make this video, it's, I think, Appendix B. You can check me on that. And you will see that there is a list of standard entropies. So standard entropies are entropies under standard conditions. Temperature of 25 Celsius, which is 298.15 Kelvin. Pressure of 1 atmosphere or 1 bar, depending on how old your thermodynamic data is. People are switching over to 1 bar from 1 atmosphere. And these numbers are absolute. This is not delta S, the way that you'll find delta H in those same thermodynamic tables. These are actual entropies. And we're going to use those in our next video. So entropy is a thermodynamic property of matter that measures possibilities of how that matter can be moving, rotating, vibrating, and just be positioned. And that is something that we can actually calculate as a number. I hope this was helpful, and I will see you again soon.